Hi everyone. In continuing with the states of matter, in the previous class we have discussed the experimental gas laws. After this we have gone through the equation of state, ideal gas, the concept of ideal gas, and how this ideal gas equation can be used for solving numerical problems that we have demonstrated or discussed. So after this we are going to take up the partial pressure. Though already we have discussed the concept of pressure in Charles law, but still we have to confirm more on this partial pressure and the laws governing the partial pressure. So the heading for today's discussion will be Dalton's law of partial pressure. So before discussing what is Dalton's law of partial pressure, we need to define or we need to understand the concept or the meaning of partial pressure. So let's define the partial pressure first. Now the meaning of the partial pressure is, suppose we have a mixture of gas, and in this mixture of gas we have different number of molecules of gas on the same. Now these molecules of gas of different type will have individual pressure, means the individual contribution of a particular gas in a mixture of gas. So whenever we have a mixture of gas, there will be contribution of each and every individual gases to the total pressure. So what is the contribution of a particular gas to the total pressure of the gas? That pressure is known as the partial pressure. So we define this partial pressure as the pressure exerted by the molecules of a gas in a mixture of gases. That is known as the partial pressure. That is the pressure exerted by the molecules of a gas in a mixture of gas, that is the individual contribution of a particular gas in a mixture of gas, that is known as the partial pressure. So this Dalton's law is for this partial pressure. That means we have a mixture of gas in a container and each gas is having some individual pressure which is known as partial pressure. So how this total pressure is related to the partial pressure of individual gas, that is governed by a law which is known as Dalton's law. So to understand this Dalton's law, let's take this help of this diagram. Suppose we have a container. This container, the total volume pressure is T, that is total pressure. This container is having a volume of B and temperature T. That means all the gases that is present inside this case are at same volume and same temperature condition. Suppose we have A gas plus B gas plus C gas. So this container contains three different gases A, B and C, and there is no chemical reaction occurring between A, B and C. That means this A, B, C or the number of gases which is present inside this container should be non-reacting gas. So we have non-reacting gaseous mixture. Now the number of moles of A, B and C gas B, Na, Nb and C. This is the total number of this is the number of moles of gases A, B and C present in this mixture. And the partial pressure of A, B and C, B, PA, PB and PC. So we have this as a partial pressure of A, B and C, that is a non-reacting gaseous mixture present in this container, which are maintained at temperature T and volume is V. The total pressure of the gaseous mixture is PT. If this is the condition, then according to Dalton's law, the total pressure of the non-reacting gaseous mixture is equals to the summation of the partial pressures of the gases present in the mixture. So we have a mixture of three non-reacting gases, each having partial pressure of Pa, Pb and Pc. Then according to this law, the total pressure of the gaseous mixture is equals to the summation of the individual partial pressure. This is what we call as Dalton's law of partial pressure. So for this very important requirement is all the gases must be maintained at same temperature and same volume, and there should not be any reaction between the gaseous molecule. So this is Dalton's law of partial pressure. So I repeat the sentence. According to this law, if in a mixture of non-reacting gases, the total pressure exerted by the gaseous mixture is equals to the summation of the partial pressures of the gas. Now we have defined a term which is known as partial pressure, that is the pressure exerted by the molecules of a gas in the total gaseous mixture. So we have to define this partial pressure mathematically. Now the partial pressure of a gas in a mixture, let this be Pi, this is the partial pressure of ith component in a mixture, is equals to the mole fraction of the ith component into the total pressure, whereas Pi is partial pressure of ith component in the mixture, where Xi is the mole fraction of ith component in the mixture. So the partial pressure is mole fraction into the total pressure. Now from this we can define this mole fraction. So mole fraction is equals to partial pressure divided by total pressure. This ratio is defined as the mole fraction. In the first chapter, that is in the basic concepts, we have defined the mole fraction as number of moles divided by total number of moles. So number of moles of any given component divided by total number of moles, that was also defined as mole fraction. But in terms of this Dalton's law of partial pressure, if the pressure of individual gas and the total pressure is known to you, then the ratio of partial pressure to that of total pressure, this is also defined as the mole fraction. So now this is the relation between mole fraction and the partial pressure of the individual gas. So partial pressure is mole fraction times the total pressure, or the mole fraction is equals to partial pressure divided by the total pressure. So So this is partial pressure, the concept of partial pressure, and Dalton's law. As I told you, Dalton's law is applicable for non-reacting gaseous mixture. If this reacts, or if there is any chemical reaction between the components A, B and C, then the law will not be applicable. So look at this, I am just giving the examples here. Hydrogen gas plus chlorine gas. Suppose we have a mixture of these two gas, hydrogen gas and chlorine gas. Now these hydrogen gas and chlorine gas reacts to form hydrogen chloride gas. Now look at this. Whenever we have a mixture of hydrogen gas and chlorine gas, this always reacts to give you hydrogen chloride. Now since this reaction mixture, in this reaction mixture, Dalton's law of partial pressure will not be applicable because there is a chemical reaction between hydrogen and chlorine. Whereas Dalton's law of partial pressure says this has to be a non-reacting gaseous mixture. Take this, we have oxygen gas and helium gas. So in this mixture of gas, Dalton's law will be applicable because there is no chemical reaction between this oxygen and helium. Take this, oxygen and neon, again Dalton's law will be applicable. Take this, hydrogen gas and helium gas, again for this reaction mixture Dalton's law will be applicable. Take this, ammonia gas and HCl gas. So we have a mixture of ammonia gas and HCl gas. Whenever this ammonia gas comes in contact with HCl, it immediately combines to give you ammonium chloride, which is solid. This is white color solid. Though we have a mixture of ammonia gas and HCl, but immediately this reacts to give you ammonium chloride, which is white color solid. So this Dalton's law will not be applicable to this mixture. Take this ammonia gas plus HBr gas. Again this reacts to give you ammonium bromide, which is again a solid. So again this mixture Dalton's law will not be applicable. Similarly, look at this, we have this ammonium, so ammonia gas plus HI gas. Again this reacts to give you ammonium iodide, which is again solid. So again Dalton's law will not be applicable. So why I am saying this? For this Dalton's law to be applicable, the gaseous mixture should be a non-reacting gaseous mixture. If at all this undergoes chemical reaction between the components of the mixture, then Dalton's law will not be applicable. So this is what we call as Dalton's law of partial pressure. Then while discussing this, again one term comes that is known as aqueous tension. Aqueous tension. Aqueous tension is the partial pressure of water vapor. Aqueous tension is known as the partial pressure of water vapor. So whenever we have gases are taken as a moist gas. So therefore look at this, pressure of moist gas, that means a gas which is dissolved in water. So that is known as partial pressure of the moist gas. So the partial pressure of moist gas is equals to the partial pressure of dry gas plus aqueous tension so therefore aqueous tension, that is the partial vapor pressure of water, is equals to P moist gas minus P dry gas, or partial pressure of dry gas will be equals to P moist gas minus aqueous tension. So just from formula point of view, just remember this: whenever we have to apply ideal gas equation, we have to apply this ideal equation only for dry gas, not for the moist gas. So if you are having a moist gas, then this should be converted into dry gas. For this, dry gas is equals to moist gas minus partial pressure of water vapor, or which is known as aqueous tension. Now, based on this partial pressure, let's try to solve some numericals. Let's see how we can use this find this partial pressure or total pressure, provided partial pressure is known to you. Suppose question says dry air contains 78% by volume of nitrogen and approximately 21% by volume of oxygen. That is, we take a sample of dry air, yes, having a volume V. In this volume V, 78% volume is for nitrogen gas and the remaining 21% is for oxygen gas, and the rest approximately 1% or less than 1% is for the remaining gas. So we are having a dry air. Now, if normal atmospheric pressure is 1 bar, then find partial pressure of nitrogen and partial pressure of oxygen gas. While discussing Dalton's law of partial pressure, we define partial pressure as mole fraction into total pressure. So therefore, look at this. Question says normal atmospheric pressure, that is the total pressure of dry air, is 1 bar. Then we have to find partial pressure of nitrogen. To define this, we need to have mole fraction of nitrogen into total pressure. Total pressure is already given as 1 bar. We need to find the partial pressure. So we will look at this. Partial pressure of oxygen is equals to mole fraction of oxygen into total pressure. Again, we require the mole fraction of oxygen here. Now, question says the volume percent. The question says volume percent is equals to mole percent or mole percent, which is nothing but mole fraction. So please keep this in mind. Volume percent is equals to mole percent, which is nothing but the mole fraction. So just to confuse, this is given in terms of volume percent. So this volume percent is equals to the mole percent, or that is mole fraction. So therefore, the mole fraction of nitrogen is 0.78 and that of oxygen is 0.21. So 0.78 into 1 bar. This is 0.21 into 1 bar. So this is the partial pressure of nitrogen and oxygen in dry air whose volume percentage is 78% and the 21%. So this is how we use the concept of partial pressure or the volume pressure in terms of mole fraction. So look at this question. Pressure of 1 gram of an ideal gas A at 27 degrees centigrade is 2 bar. When 2 gram of another gas B is added in the same flask at the same temperature, pressure becomes 3 bar. Find the relationship between their molar mass. So look at this question. Says we have a container. This container volume is V. So this case 1 says we have a gas which is 1 gram and the pressure of A in this container is 2 bar. This is temperature of A is 27 degrees centigrade. Now what we are doing is, to this we add 2 grams of B, that is the container is same volume. This contains A plus B. We have 1 gram of A and 2 gram of B. Total pressure becomes 3 bar. Total pressure becomes 3 bar. Then question says the relation between their molar mass. Temperature is still remaining same. Temperature is still 27 degree centigrade. So find the relation between the molar mass of the gas A and B. Now first of all look at this. We have a mixture of A and B. Total pressure is 3. Pressure of A when it was present alone in the same container under the same temperature condition comes out to be 1 bar. So the partial pressure of A is 2 bar. Then we have to find the partial pressure of B. So if you look at this, mass of A, that is 1 gram, then let the molecular mass of A be Ma. So therefore number of moles of A will be Wa by Ma. So we said this is 1 by Ma. Mass of B introduced in the sample is 2 gram. Let the molecular mass of B be Mb. Then number of moles of B will be Wb divided by Mb, which is equals to 2 by Mb. Question also says the partial pressure of A is 2 bar. Total pressure, which is equals to partial pressure of A, because this contains A and B, so therefore according to Dalton's law, total pressure is partial pressure of A plus partial pressure of B. So therefore partial pressure of B is equals to total pressure minus partial pressure of A. Total pressure is 3, partial pressure of A is 2, so this is equals to 1 bar. Now question clearly says both the gas A and B are ideal gas. Now we can use the ideal gas equation. From ideal gas equation we say P A V A is equals to NAR TA, that is equation 1. Similarly PB into VB is equals to NV RTB. Now taking this ratio, divide A by B, we have PA VA divided by PB VB is equals to NARTA divided by NBRTB. If you look at this, volumes are same, temperatures are same. So since temperature is same, so TA TB will cancel out. R is a constant, so both are cancel out. volume VA and VB are same. So therefore we have this ratio. Pressure of A divided by pressure of B is equals to number of moles of A divided by number of moles of B. We have this number of moles of A and B, that is WA by MA divided by WB by MB. So this is 1 by MA and this is 2 by MB, or we shall look at this PA by PB is equals to half into MB by MA. Now we have partial pressure of A and B. So partial pressure of A is 2, partial pressure of B is 1. So this is equals to half into MB by MA, or we can say MB by MA is equals to 4, or we say molar mass of B is 4 times molar mass of A. So all this problem can easily resolve provided we know the partial pressure of Dalton's law of partial pressure. What is the concept of partial pressure? So we have, from this total pressure we have defined the partial pressure of B, because already we know when this contains only gas A, the partial pressure of gas was found to be 2 bar. So this is how we use the concept of partial pressure in solving numerical problems. Now, having gone through the concept of the partial pressure, now we are going to discuss a new concept that is known as diffusion or effusion of gas. So the heading is diffusion, effusion of gas. So for this, first we have to define what is diffusion and what are the conditions required for this diffusion. Then we'll separate what is effusion. So from lower class we have been using the word diffusion of gas. Gas has a very good tendency to undergo diffusion. The base example is when we use perfume, the smell of perfume can be felt at a larger distance. Similarly, during puja, we use incense sticks, agarbatti. You lit agarbatti and place in a corner of room, and the smell of that agarbatti can be felt throughout the room. So we say this property of gas is what we call as diffusion. Now the question is, what is diffusion? So diffusion is intermixing of gases on its own due to partial pressure difference. So this intermixing of gas due to the partial pressure difference is known as diffusion. So diffusion is intermixing of gases due to partial pressure difference. So this intermixing goes on till the partial pressure difference drops to 0. So whenever we have larger partial pressure difference between the gases to be mixed, then the rate of diffusion will be faster. As the partial pressure difference decreases and drops to the equilibrium state when the partial pressure of both the gases are same, the rate of diffusion becomes almost 0. So therefore look at this diffusion, this intermixing is possible only when there is a partial pressure difference. So the condition required for diffusion is there must be partial pressure difference. Must the partial pressure difference. Or there must be difference in the densities of the gases to be mixed, or difference in densities. So whenever we have difference in the partial pressure or difference in the densities, these gases will undergo mixing, which is known as diffusion, and this goes on till the densities are same or till the partial pressures are same. And we know, look at this, gases always move from high pressure to low pressure. So keep in this mind, whenever we mix the gas always flows from higher pressure to the lower pressure. So as the gas flows from high pressure to low pressure until a difference becomes zero, this keeps on mixing. When the difference is zero, the mixing will stop, means this intermixing will stop. So rate of diffusion depends on the partial pressure difference. So now the question is, why look at these gases, though we have a partial pressure difference or density difference, but what is the reason behind this intermixing due to partial pressure difference? Now look at this, we say in case of gases molecules, there is a large gap between the molecules. So when we say the intermolecular distance between the gas molecule is very high in case of gases, so there is some unoccupied space, so the third molecule of gas can enter it. Yes. So this intermixing is due to a phenomenon which is known as, due to the presence of large unoccupied space between the gas molecules. This unoccupied space, the third molecule can easily enter into, and this is the reason why there is diffusion of gases. Now we also have a term which is known as effusion. Effusion. So diffusion is a general term. Any intermixing of gases is known as diffusion. But if diffusion occurs through a small pinhole, if the movement of gas is through a small pinhole or a small orifice, then that is what we call as effusion. Leakage of gas into vapor, also into vacuum through a pinhole or small orifice is known as diffusion. So we have a container, this container contains a gas. Now to this container having gas, a small pinhole is made and the gas is allowed to escape in a vacuum. That is the leakage of gas into vacuum. So this movement of gas molecules through a very small pinhole or a small orifice or small opening, this is known as effusion. So effusion is specific diffusion through a pinhole, whereas diffusion is any general intermixing of gases molecule is known as diffusion. Okay. Now this rate of diffusion, let this be R. So rate of experimentally this is found to be equals to PA 2 pi mRT. But this P is the partial pressure difference A, area of pinhole, M, molar mass of the gas, R, gas constant, T, temperature of the gas measured in terms of Kelvin. So looking at this equation, R is equals to PA divided by under root 2 pi mRT. Rate of diffusion is directly proportional to the partial pressure, as we have discussed earlier. This diffusion is due to the presence of partial pressure difference. So if there is a partial pressure difference, the difference between the partial pressure of gases to be mixed is large, then the speed of intermixing will be fast. If the partial pressure decreases, then the speed or the rate of intermixing of gases will be less. The rate of diffusion is also directly proportional to the area of orifice. If the area of the small opening through which gas molecule is to be moved, if area is large, larger molecules can easily move. So that means rate will be fast. If area is very small, a very small amount of gas molecules will move, the rate of mixing or the movement of gas molecules will be less. So we say that rate of diffusion or effusion is directly proportional to area of orifice. Second, look at this. The rate of diffusion or effusion is inversely related to the molecular mass. Let's visualize in this way. A heavier gas will move slowly and a lighter gas will move fast. So as the heavier gas moves slowly, the rate of intermixing, and that is the rate of effusion or diffusion, will be less. Now if the mass of the gas is light or less, then this can move fast. As the gas molecules moves fast, the rate of effusion or diffusion will also be fast. Now take temperature. If we increase temperature, the kinetic energy possessed by the gas molecules will be more. If the kinetic energy of the gas is increased, the velocity of gas molecules will also increase. If the velocities of gas molecule increases, these gas molecules will move faster. As the gas molecules moves faster, the rate should have been faster, but in this equation, the rate is inversely related to temperature. If the temperature of the gas is increased, the rate of effusion or diffusion is decreased. So the meaning here is, if we increase the temperature, no doubt kinetic energy of the gas will increase. If the kinetic energy is increased, the value of the velocity of gases will also increase. If the gas molecules moves faster, then the collision between the gas molecules will also increase. Due to this collision, molecule will have less time for orientation, so that this is passing through the small orifice. Is it clear? So as the molecules undergoes large number of intermolecular collisions, because of this faster movement, collision becomes more. So the more the gas undergoes collision, it will have less orientation for passing through this small pinhole. So the number of molecules passing through this pinhole of area A will be less. As the number of molecules passing through this small pinhole is less, the rate of effusion or diffusion will be less. If the area of opening is large, then on increasing temperature, rate will increase. We are discussing for a very small pinhole through which gas molecule is to be passed through. So this is the rate and its dependence. Now for a given gas at same temperature and pressure, at same temperature and pressure, these are rate can be written as pressure is a constant, area of opening is a constant, 2 is a constant, pi constant, r constant, t constant. then this can be written as some constant K into 1 by square root of molecular mass. So for any given gas at a constant temperature and pressure, rate is inversely related to its molecular mass. So therefore look at this, suppose we have a gas molecule Ra, so this is K by under root of Ma. Another gas molecule at the same temperature and pressure, rate is K by Mb. So therefore the ratio of rate of diffusion Ra by Rb is equals to Mb by Ma. This equation is known as Graham's law of diffusion. So according to Graham's law of diffusion, for two different gases at the same temperature and pressure, the ratio of rate of diffusion is inversely related to the ratio of their molecular mass. This is, that is the equation 1. So ratio of rate of diffusion of two different gases is inversely related to the ratio of their molecular mass, provided temperature and pressure of the two gases remaining constant. So this is for same temperature and pressure condition. Now this equation can be modified for ideal gases. Now we have defined ideal gas. Look at this. For ideal gas we define this as P is equals to density RT by molecular mass. So therefore we can say Pm is equals to density RT. So therefore look at this, molecular mass is directly proportional to density provided pressure and temperature is a constant. So we can say, look at this, therefore molecular mass is directly proportional to density if pressure and temperature remaining constant. So look at this, this is having same pressure temperature condition. Under this condition, molecular mass is directly proportional to density of the gas, so we can replace this. So therefore from equation 1, Ra by Rb is equals to Mb by Ma. Molecular mass is directly proportional to density, so we can say this density of gas B divided by density of gas A. So again we say rate of effusion or diffusion under constant temperature and pressure is inversely related to the densities of the gas. So the gas with higher density will have lower rate of diffusion or diffusion. Now look at again this. In the previous chapter, that is the first chapter, we have defined a term which is known as vapor density. So vapor density of a gas is equals to half of molecular mass, or we can say molecular mass is equals to 2 times its vapor density. So we can also replace this molecular mass in terms of the vapor density, provided the vapor densities of the gas are mentioned to you. So therefore Ra by Rb is equals to Mb by Ma square root. So Mb and Ma. So we have molecular mass is 2 times vapor density, so 2 will cancel out. So we have vapor density of B divided by vapor density of A. So this is equals to density of B divided by density of A. So we say the rate of diffusion or effusion is inversely related to the vapor densities of the gas. So ratio of the rate of diffusion is inversely related to the ratio of the vapor densities of the gas. If the densities are given, we have this. So this is Graham's law of diffusion. Apart from this, the rate of diffusion or effusion can also be defined by a number of terms. So let me just give you some other definitions of effusion or diffusion. Some other definitions of diffusion or effusion. Rate of effusion or diffusion is equals to volume of gas diffused per unit time. Volume of gas diffused, this is time in per terms of second. So volume of gas diffused per unit time, this is also defined as rate of effusion or diffusion. This is also defined as N by T, where N is number of moles of gas diffused. So number of moles of gas diffused per unit time is also defined as rate of diffusion. This can also be defined as W by T, where this W is the mass of gas diffused. Mass of gas diffused per unit time. This is also defined as D by T, where D is the distance traveled by the diffused gas per unit time. Distance traveled by the diffused gas per unit time. So the rate of diffusion is equal to volume diffused per unit time, number of moles of gas diffused per unit time, mass of gas diffused per unit time, distance traveled by the diffused gas per unit time. So if volume or number of moles or mass or distance traveled by the diffused gas, this is given to you, then we can define this rate of effusion, diffusion in terms of these parameters. Or if nothing is defined, then this ratio of rate of diffusion will be defined in terms of molar mass, or in terms of density, or in terms of vapor density. So this is the concept of diffusion or effusion and conditions required for diffusion, effusion, what this diffusion, effusion really means, and what is the rate of effusion, diffusion. So under specified condition of temperature, pressure, we define a law which is known as Graham's law of diffusion, and add some other definitions of diffusion. So using this, we'll try to solve some example problems. So let's see how we can use this definition of effusion, diffusion to solve the problems. So look at this question. 20 decimeter cube of sulfur dioxide diffuses through a pinhole in 60 seconds. What volume of oxygen gas will diffuse in 30 seconds under similar conditions? So similar condition means temperature and pressure remaining constant. So what will the volume of gas that will diffuse in 30 seconds? So data says volume of sulfur dioxide gas diffused, that is 20 decimeter cube, and time required for this diffusion of sulfur dioxide is 60 seconds. Question asks to find out what is the volume of oxygen gas that will diffuse in 30 seconds. In both the case, temperature, pressure remaining constant. So look at this, we have been given volume and time, we have to find the volume. So look at this. Molar mass of sulfur dioxide is 64. Molar mass of oxygen, this is 32. Now take this ratio. The rate of sulfur dioxide divided by the rate of diffusion of oxygen is equals to under root of molar mass of oxygen divided by molar mass of sulfur dioxide. This is from Gram's law of diffusion. Now, from the definition of rate of effusion or diffusion in terms of volume per unit time, so we define this as volume of sulfur dioxide divided by time of sulfur dioxide divided by volume of oxygen divided by time of oxygen. So rate in terms of volume per unit time. So this is volume of SO2 into time of oxygen divided by volume of oxygen into time of sulfur dioxide. So look at this. We have molar mass, we have time and volume of sulfur dioxide. So we can easily find the VO2. So compare these two. So both are same. So therefore VSO2 by VO2 into TO2 by TSO2 is equals to under root of molar mass of oxygen divided by molar mass of sulfur dioxide. So use the values. Volume of sulfur dioxide is 20 decimeter cube. Time of oxygen is 30 seconds. We have to find the volume of oxygen. Time for sulfur dioxide is 60 seconds. Molar mass of oxygen is 32. Sulfur dioxide is 64. So we have 2. So we have this. So therefore look at this. 10 by volume of oxygen is equals to, so therefore volume of oxygen is equals to 10 divided by 1 by root 2. So we have to find this value. So this is the volume of oxygen gas that will diffuse in 30 seconds. This must be in terms of decimeter cube. So this is how we define diffusion, rate of diffusion by use of these definitions. Look at this question. Question says calculate the rates of diffusion, that is the relative rates of diffusion of uranium hexafluoride, that is 235 isotope, uranium hexafluoride 238 isotope in gaseous state. So simply says the ratio of rate of diffusion. So is R UF6 235 divided by RUF6 238 will be equals to the molar mass of UF6 238 divided by molar mass UF6 235. So mass of uranium is given as 235 or 238, fluorine is 19, we can easily find. So atomic mass of fluorine is 19 U. So we can easily find the molar mass, and with this ratio, this is the rate of diffusion or diffusion of these two gases. So this will be slightly greater than 1. So let's look at this question. 1 mole of nitrogen at 0.8 atm takes 38 seconds to diffuse through a small aperture, whereas 1 mole of an unknown gas of unknown compound of xenon with fluorine at 1.6 atm takes 58 seconds to diffuse. Calculate the formula of the compound. So we have to define the formula of the compound which is formed between fluorine and XF. So let's see, let the formula of compound be XeFX. We have to define this X. Once we know the value of X, we can easily define. Question says number of moles of nitrogen is 1. Number of moles of XeFX is 1. Time required for diffusion of this nitrogen is 38 seconds. Time for this XeFX6 is 50 second. Pressure of nitrogen is maintained at 0.8 atm. Pressure of this unknown gas XeFX, this is maintained at 1.6 atm. So we have to find the formula of the compound. Now look at this, we have this ratio of rate of effusion diffusion, RXeFX divided by Rn2. This is equal to, because look at this was directly proportional to pressure. You have to look at the pressure is not constant. These are at pressure, different pressures. So we have to look at this pressure of XeFX divided by pressure of N2 into molar mass of nitrogen divided by molar mass of XeFX. So this must be equals to N XeF6 divided by T XeFX into T N2 by N2, because we define rate of diffusion as number of moles of gas diffused per unit time. So number of moles of both are same, so this can be cancelled out, because look at this, both are 1 mole. So from this what we can find is the molecular mass of the unknown compound. So therefore look at this, T N2 by TXeFX is equals to PXeFX divided by PN2 into molar mass of N2 divided by molar mass of this unknown compound. So time for diffusion of nitrogen, that is 38, divided by time for diffusion of the unknown compound is 57. So this equals to pressure of this unknown is 1.6, pressure of nitrogen is 0.8 into molar mass of nitrogen is 28. Let this be the M. So we have to find the value of M. So take the square. So we have 38 by 57 square is equals to 4 into 28 divided by M. So therefore molar mass of unknown compound is 4 into 28 into 57 square divided by 38 square. Now look at this. Suppose this is having some finite value. Let this value be A. So this is the molecular mass of the compound XeF6. Atomic mass of xenon is suppose 131. I suppose this is the atomic mass of xenon. So therefore look at this, molecular mass of XeFx is equals to A, but this must be equals to 131 plus X times mass of fluorine is 19. So from this we can easily define the value of X. So 19X plus 131 is equals to A, or therefore X is equals to A minus 131 divided by 19. So we find the value of X. So this, once we have the value of X, we can easily define the formula of the unknown compound, that is XeF6. So this is how we use the concept of the rate of effusion or diffusion for solving problems. So this is all about the Gram's law and the concept of effusion and diffusion.